All right. Hello, welcome back. Um, the only thing that I have left before wrapping up this Newton-Euler dynamics is a special case of that happens quite a lot in the systems in the dynamical system we are working with, and that is rotation of bodies that have this axial symmetry. So you can think of shafts and discs and anything that when you rotate it looks the same. And those actually happen to rotate about that axis quite a lot. So it's a common situation. And here we want to see if we can change our perspective a little. Can we improve the equations of motion in a way that we can work more easily with them? So that's the topic of this video. So let me go back in time a few videos ago. So imagine I have my body and I have, I don't know, some random fixed body frame, and my body is happily rotating about some axis omega. That is not a good axis. That's maybe better. All right, so in this case, well, not in this case, in any case, in any general case, in the most general case, that's what I want to say. The rotational equation of motion is h dot equals m. So the rate of change of angular momentum of the body equals the net external moment acting on the body. So this is very general, and because it's too general, usually we don't work with that form. It's just not useful for most of cases. What we did last time was considering this vector of h that we are trying to find its total derivative with respect to some inertia frame. We changed our perspective. We used an intermediate frame that was the body fixed frame, and in doing that, we could write h dot equals h dot relative, how an observer that sits and rotates with the body sees how that vector changes, plus omega cross h. And because the frame was fixed to the body, this omega was actually the same as angular velocity of the body. So this works, and we worked with it. We continued a bit. We derived Euler's equations. If you don't remember, 3-4 videos ago. But this doesn't have to be this intermediate frame. Doesn't have to be body fixed. It can be anything, as long as it's some arbitrary frame. We can write these terms in that frame. We should be good. So if this rotating frame doesn't need to be a body fixed frame, and we can be a little clever on choosing what relative frame we are considering, such that we may take advantage of some of the geometries in our system. One particular case that we are interested in this condition is systems with axial symmetry. So let me draw this. What's happening? So as always, this is my inertia frame, and I have something like a disk, or I don't know. It could be anything as long as it has symmetry. Let me make it like a funnel. Doesn't have to be a disk. It's a funnel rotating about its axis. Yeah, that's actually nice. So what I can do, well, before that, so this body has a very nice symmetry. So about its axes, this is its main axis. If we consider, let me think. Well, maybe not the best kind of example. No, it is good. So about this axis, and maybe let me add a couple of two more axes. So a different color. This is one axis. This is another one. This is the third one. So these are principal axes for this body because of the symmetry. Really doesn't matter. So let's look at this. So this is my body with axial symmetry, just a disk. And this is my XYZ frame. Doesn't matter really what direction I consider. All the moments of inertia about any of these will be identical because it's equivalent of rotating the body appears identical to the observer in that frame. So in that case, all products of inertia are xy equals iyz equals izx equals 0. And my products, moments of inertia, let me label this one as x. The important one, this one, let's call it y, let's call this one z. So Ixx, which is the axis of symmetry for this body, the moment of inertia about that, let's call it Ia for axis. And the other two, Iyy and Izz, because they are looking at essentially the same thing, the moment of inertia about these two axes are the same, and let's call it It. So that is about the moment of inertia of the system. Now, instead of fixing, so this is again my body, this is my frame, and my body is rotating about maybe this axis, axis X. So before, what I was doing, I was fixing the frame to the body, so everything was rotating together. So in any direction it was going, it would the frame and the body would be fixed and rotate together. Now what I can do is allow essentially for the body to spin about x-axis without me rotating my xyz axis. So this additional degree, kind of not degree of freedom, but possibility of body rotating about x-axis is what makes this formulation different. And if we do that, now we allow the body spins about x axis with some rate s. So s is the kind of the spin rate about x-axis. And remember that the frame is essentially tracking the center of the body, but does not rotate with it does not rotate with it when the body rotates about its axis. So in that case, the angular momentum of the body is very similar as what we had before. So let me bring it here again. So still, as the body rotates in space, I have the omega x, omega y, and omega z of just the frame that tracks the axis of rotation. And on top of that, the body also spins with an additional s about the x-axis. So the angular momentum, before we had omega x I plus omega y j plus omega z k. I'm sorry. I need IA times this, IT times that, IT times that. Before we had this, now that we are allowing the body to spin, we have just an additional rate about x that the body is rotating about. So that is my angular momentum. And in this case, I'm going to call omega x plus s as some total rate of total spin. So let's call it total spin. And going in the same direction that we had before, and I have it up there too, h dot relative, given the same argument that we had before, is only now IA times omega dot x plus s dot I plus IT omega dot y plus IT omega dot z k. And with these, my h dot total h is going to be this h dot relative that I calculated plus omega c cross h, the one I calculated up there. And the difference with the previous calculation is that now this omega c is not the rate of rotation of the body. So the body, remember, rotates with an additional spin about x-axis, which is not included in this omega c. So omega c is just omega xi plus omega yj plus omega zk. The angular velocity of the frame, as it just tracks how the orientation of the body, the axis of rotation, is changing. And if you use this equation now to find the Euler equations, it's going to be kind of similar, except that now I don't have any products of inertia, and two of my moments of inertia are also equal to each other, so that we called it IT. And from here, I have IA, the axial moment of inertia, times omega dot x plus s dot, which we call it big omega dot IA, equals mx, moments about x, IT omega dot y minus IT minus IA omega z omega y equal, wait, I'm missing one term, plus IA s omega z equals my, and IT omega dot z plus IT minus IA omega x omega y, is that minus? Yeah, minus IA S omega y, yes, I hope so, equals mz. So these are called modified Euler equations. And the only real difference between these equations and the previous Euler equations that we found is that now we are allowing this additional s. So if you keep s to be 0, essentially engaging a clutch between your frame and your body, you engage that brake, s is 0, put s equals 0, you recover exactly the same equations that we had before. But now, because of this additional possibility that the body rotates, this formulation can actually lead to significantly simpler ways to try to track how the axis is rotating, because now you don't have to rotate about this fast rotation of the frame about the axis of rotation. You can let the body rotate nice and easy about that, and only track motions that are potentially simpler to model and calculate. Yeah. So although it may look a little unintuitive and it's just another set of equations, we will solve an example in class that we'll see how different it is from the original Euler equations for orientation. Okay, I think that is all I have for this video. Let me see. Yeah, that is all I have. So with this, we wrap up the Newton-Euler kind of equations. We have a little bit on Lagrangian related to rigid bodies. And then we will go into multi-body dynamics, so system of rigid bodies. So until then, happy studying.